accurate and rapid modeling of automotive networks and gateways. I'm your host, Deepak Shankar, and I'm one of the founders of Mirabilis Design. And today I'll be walking you through the innovations and capabilities that we at Mirabilis Design have put together to accelerate product development in the automotive industry. We're going to start off with the traditional network modeling approaches, look at what is required or what has changed since that time, and go through examples, the methodology, and also some experiments associated with this industry. Now, if you look at the traditional automotive network, typically they had one type of protocol, could be a CAN or maybe a flex rail LIN, with one or two gateways. So fairly simple, considered where network latency and throughput for the purpose of assigning sensors and ECUs across the network segments. And the routing table is configured to ensure that there was deterministic time between all the transfers of either signals or messages. And to be able to find the network bottlenecks, where do I need to increase capacity? Where do I need to reduce the number of sensors, things like that. So that was your traditional auto networking analysis and simulation. The new generation looks completely different. As you can see over here, there are more communications outside of the vehicle than there is within the vehicle. So for example, you have wireless and wired, you have access to data centers, access to toll gates, access to pedestrians, access to traffic infrastructures, other vehicles. In addition to everything that's inside the vehicle, be it safety, engine, braking, infotainment, autonomous driving, any of those kind of information. So that's on the network level. Then there are application levels. For example, autonomous driving. It needs to receive data within a fixed time frame concurrently from local sensors, from the cloud, and through V2V from road infrastructure. So processing is both distributed and also has significant data movement between all the ECUs. Now, on top of all of these, there are new applications, requirements that have evolved. For example, cybersecurity is a major requirement that has to be evaluated. As a result of that, a lot of artificial algorithms are there for optimal routing, for threat detection, for autonomous driving, activities such as those. So to review all of these, there's a lot of failure scenarios, protection scenarios that you may want to look at. And of course, the processing availability now in a vehicle is substantial, which means you can dynamically reallocate processing depending on where the requirements are. Say autonomous driving needs more data, or for example, infotainment needs. The processing can be moved dynamically across these different ECUs. I know that in the future, there's also considerations of having single servers like in aircrafts that can handle all the heavy lifting load and then all the local sensor processing, which is like filtering and things that can be done locally by the ECU. So a lot of different combinations of computers are occurring, which means the network is also evolving. Now, in addition, within the network itself, there are new types of technologies. Security gateway is a very good example where you're no longer providing security within the vehicle, provide security outside the vehicle. Going into like home networks or, incorporating a Wi-Fi or, looking at telematics. A lot of information that's going outside of the vehicle, which could be hacked. So security gateway is another new product. And of course, within the car itself, there are a lot of technologies that have evolved. Apart from autonomous drive, infotainment systems are now tightly linked to safety, tightly linked to comfort, into security in the event of an accident, things such as those. Now, when you look at the VisualSim networking solution, there are two main areas that we focus on just for the networking, and then I'll talk about all the peripherals around it. First is background of communication architectures are really there to reduce the wiring weight, going from like 1,000 pounds down to 10 pounds. And the other thing is to support the huge amount of data that's going to be going across to migrate to time-sensitive networking, especially for CDT or control data packets for time-critical processing at the gate. Using VisualSim, there are two things you can do. One is observe the behavior of both deterministic and non-deterministic traffic across the CAN Ethernet gateway, but also be able to configure things like the credit policies, the time slots, the buffers, the processing requirements, and the software allocation across the ECUs. Now, let's take an example of a gateway so we understand really what is happening there in VisualSim. First and foremost is you can see the libraries on the left-hand side. These libraries are utilized in the model by dragging and dropping them and instantiating them within the model. And each one of these library components, for example, you can see the Ethernet node has a specific and unique set of parameters. Similarly, other modules like CAN bus or gateway or things like that would have their own set of parameters. So if I open up VisualSim right now to take a quick look, this is the modeling environment. So you can see the networking components, you can see traffic components, and then you can, and using these, you can assemble up the full system model. So for example, if I double click on this, shows me all the parameters associated with and with CAN-FT. Similarly, if I look at the gateway has a unique set of parameters. Similarly, the TSN switch has its own set. So each block has its own unique set of parameters that are used to actually come up with the specification of your particular design. So for example, if I click on this go button, a variety of plots and displays are going to come up. Some of you related to the different channels, what is the latency? You can see, and similarly, you can also see end-to-end latency. In this particular design, what you're seeing is the end-to-end latency is constantly increasing, which apologize for that short delay. What you're seeing over here is that there's a variety of statistics that are generated as part of the model one. For example, over here, you can see the latency across different channels. So from channel 1 to channel 2 across the gateway, or channel 23 to 22. What was the latency for each one of those channels? This shows you what my end-to-end throughput is, which is this particular case goes to about, I think about 10 gigabit per second of data, which is showing me what the throughput is over the period of the simulation. This one here is an interesting chart because what it's showing me is what is the latency over time. And as you can see, the latency is increasing, actually starts decreasing right there, indicating that there's substantial amount of buffering across the network. So it could be because of scheduling, or it could be because of buffering, or because of lack of bandwidth. That's something that we're going to analyze over time. Other kinds of statistics show you, where the input outputs are, what are the throughputs across different resources. Then you can see, for example, the going across the end-to-end. So you can see from your Ethernet, going across the network to arbitration, to all the individual components across a particular system. So it gives you that kind of statistics as well. Plus, it gives across the data. You can see these are very low amount of data, while 23 to 22 is extremely high. It's almost 21 megabytes of data that are being transmitted. So as you can change different parameters in the model, anything from the gateway, like, what if I make it only 100 megahertz and you run it? So how does this substantially change? So rather than going 1 gigahertz, I make it 100 megahertz, and what happens to the system is right over here. The latency is really going, most of them were over here at the point 100 milliseconds. We're now way over. We're actually like almost up to 150 milliseconds. And here, of course, you can look at what's happening to the throughput, which is earlier on was like at 1 gigabyte, is now in 700 to 800 megabytes. So big drop in the performance as well. So by varying these parameters, you can try different types of experiments and then be able to make a determination as to what is my topology, what's my configuration, what the we'll come back to it in a few minutes as we look at more of modeling and architecture exploration. Other statistics on the network itself is really latency, credit, and buffering. So here what we're looking at is, if you look at the gate control list right over here, you can see there are two slots, T1, T2, and you can see the attributes. For example, T1 slot has control data, while T2 can handle both the audio video AVB Class A, Class B, and best effort Ethernet. You can actually combine both of those into that one slot. So you can see what you can set up time periods for them, which is defined right over here. The guard band, which is right over here. So what we're looking at is the round trip delay. We expect it to be about so many milliseconds. And we want to see if that is the correct, like width of time that is required. Now, what you're seeing over here is the credit value between, the idle slopes and the, and then of course the latency here. So like, for example, here you can see the CDT, which is the red one over here. While you can see the AVB spikes, which resemble the idle slope and sense slope that's right over here, kind of matches up with these. And of course, the best effort, you can see the high latency for the best effort because there's significant amount of Class A and Class B data that are coming in at the same time as the best effort Ethernet data is coming. Of course, you can also look at the buffer occupancy at different points. You can see the Class A buffering is pretty substantial. So which means there's not enough idle slope or sense slope data, sense slope guard available for Class A traffic. That's also one of the reasons why it's being buffered. Now, let's focus specifically on the latency itself. So you can see that the total time spike in latency every 10 milliseconds. The reason is, remember we have slot one and slot two. So slot one is only this, which is your CDP data, and that's slot two, which is going up. One of the things you notice here is that the slot time is too small, right? To support these slot times such that you have sufficient bandwidth to be able to transmit the data, or you modify the traffic profile such that all of them do not show up at the same time. Now, what we're seeing over here is a much longer simulation duration, almost 500 milliseconds. And you can see these are the CDT data. But notice all of a sudden we see a huge spike. We're like at right over here in like, say, in microsecond range. And now all of a sudden we're at 9 milliseconds. Essentially, this is missing its schedule. So what happened? What we did was we changed the bandwidth, the MIF, the time-sensitive data, the CVS parameters, and we're looking at what happens in a worst-case scenario. So this is a worst-case analysis that we're trying to do and seeing how much the CDT would spike. Having said this, now we'll move over to an application example. And as I mentioned, if there are any questions, feel free to put them in the chat window and we'll be happy to answer these questions. So let's examine a TSN network. So we have the ECUs, and some of them are time critical applications. So what we want to look at is within the gateways is really understand the time aware shaper to figure out, how they can delay for the CDT frame, which is a unique type of frame on the network. Look at, what should be the idle slope, sense slopes, of the credit requirements for Class A and Class B. And here's the main one, which is what we always want to avoid, which is the buffer overflow. So we never lose data anywhere in the system. So when we look at the TSN demo, what we see over here is we see same network, and we're going to be tapping this for frame latency. And here we're going to look at the buffer occupancy, sense slope, and idle slope. So the purpose for doing that is, one is obviously, we want to look at the TSN slots. And the scientist was lines or miss up. So notice over here, it's not missing the, it actually sent it correctly. Well, the earlier scenario, which we saw on the previous slide, actually missed it, and all of a sudden now, how do we do that? One of the key things within time-aware shaping is the scheduling method. So it's important to take the scheduling method and be able to modify it in such a way that, one is, the hardware has sufficient processing capacity that it can handle the scheduling algorithm. A lot of times, algorithms are great, but because the hardware is not able to handle the workload of the software task, you get a completely different profile. So it's important to realize what should be the hardware processing. So one of the things we can do here is we want to start with looking at the latency. So, what is the latency for each of the scenarios? And then figure out, where is the bottleneck happening? So we want to compare the buffering, the latency, and the credit information to come up with how we can modify each one of those in such a way that we don't see these spikes. The spikes get completely eliminated and we don't see the buffer occupancy. Here's another one that might be useful many times is the power consumption. So in addition to looking at the network, we also want to see what the power or the energy impact of these performance decisions. So just looking at the performance, which is your latency and throughput, and configuring the scheduler, configuring the hardware platform to meet that would be a big mistake if your power is too high and your system can't handle the power requirements of the particular design. So looking at power is an extremely important attribute. Now, this is the VisualSim modeling environment, as you saw earlier. In this particular case, what we have design, we've got CAN, multiple Ethernet networks, and we have the configuration on each of the gateways. Now, one of the things we do in VisualSim is, rather than locking down the parameters in each of the individual blocks, we put these into databases. The reason for doing that is now you can store all of this in a set of files, and for each run, just modify the files without even doing any change to the model itself. So that way, like for example, I want to run a scenario where I've got multiple CDTs, or I have multiple CDT slots, and I have signals versus messaging. How does that routing get impacted as a result of the decisions that I'm making at the routing table level, or at the slot level, or at the buffer level? How does that impact my end-to-end latency? Now, let's take the gateway models. We have a gateway model here with 5 CAN interfaces and 2 Ethernet interfaces. We set up a variety of parameters. And here you can see this is how the DSM gateway architecture works, which is all of these different classes or traffic put in different queue. When they, when the gate opens for each one of them, they can come out. Now, the Ethernet interface itself that determines all of this logic and the scheduling is provided as a series of parameters that you could utilize. So the main idea here is that you can configure each Ethernet interface, each Ethernet switch and each and gateway can be configured uniquely based on these set of parameters. Now, when you're exploring with VisualSim, you want to start with the baseline. The baseline is something that just runs, but has only average amount of workload, maybe 30% or 40% of the network capacity. Now, what we're trying to do is trying to see if we keep increasing the amount of workload, increase the number of devices, increase the number of sensors, at what point does the system break down? So here, for example, you can see that this is the baseline, and that was the worst case scenario for the time-aware shaping slots. So you can actually see what should be the best case over here. And you can see that, what should be the configuration for that. So from this latency, from the profile or the activity, you can actually see what is the settings for each one of that. So gigabit Ethernet versus AVB versus CVT gives you what your slot times are. So using the VisualSim model that you saw, you could explore all of these configurations. So taking something that's a little more detailed. So here we have our, as we saw earlier, we have CDT, AVB, and our gigabit Ethernet. So our time aware shaping for 10 milliseconds and 500 nanoseconds. So you can see the slots for each one of them, how they're set up. So this is a scenario with 300 microseconds versus this one here, which is has a 50 time. It's like at 300 microseconds where it starts. This one starts at 50 milliseconds. This is in terms of the scheduling. So notice here, CDT doesn't change, but your other slot, which is slot 2, and which had the the class A, class B, and best effort, those change because here we had ABB, now we have 7BA. Now, why did A come later? It could be that it arrived later, or it could be that it didn't have enough of a credit, so it could not be transmitted. So what are the types of things we would look at? Going back to what we were looking at earlier, you can see here that the spikes are there every 10 milliseconds. So we wonder, why are those spikes occurring? That's really related to that any data coming in that time cannot transmit until that slot is completed. So the latency for AVB and best effort will go up as a result of that one. Now, the guard band is a very, very small element, so not something we should worry about. Now, because of the slots, we can see that the credit builds up to the maximum credit, which is 8,000, which the high spot in the previous slide you saw. And what happens is during this time period of the 2 milliseconds right over here, it's just building up the credit and reaches the max of 8,000. At that point, the class A, class B allowed to transmit, so you can see the rapid decrease, and then you can see that it slowly builds up the credit as well. So, every time the credit is available, the system's transmitting A and B, and when the credit dies, the system drops out the A and B. And as you can see, we start again. It starts from 2 to 10, and then 12 to 20, and you can see from here 60 goes to 62, which is the CDT, and then it goes up to 70. So you can see what the variations are right here. Now, here's the thing that's very, very interesting. At the end of every round trip, which is at 10 milliseconds, 10 milliseconds and 5 microseconds, which means should be 0.0005. So this is 1 millisecond. You can see that the huge second that indicates the data that's coming in and trying to get access. Now, these are slightly different in each of the scenarios. They're not exactly the same. And that also explains why here we had a different profile to over here. The reason is we're using a data trace that is coming in from a real network. So it's a trace file, which would have slightly different variations over time. So when you apply the slightly different variations over time, the slot usage also changes a little bit. So one of the things that's important is we're not repetitive. We're not doing the same thing in every set of slots or time-aware shaping slots, but rather there are slight variations to the traffic. So what it allows you to do is allows you to study different combinations of traffic or different time slots at time instances when the traffic arrives and what are the type of traffic. So that would determine what is happening on the network. Now, these are worst case scenarios. And as you can saw earlier, we saw this at this earlier one, you can see that the CDT frame misses the slot, which means it has to wait for the entire 10 seconds before it can start. This one had to all the way until the next slot before it was transmitting. And that's the spike that you're seeing right over here. So this is when it's on schedule and when it's short and it's off schedule. So what is happening is for this particular traffic profile, which is, we have a 8.7 millisecond slot, you can see that the CDP ends up missing the slot at different times, or at least at this 50 milliseconds, and as a result of which is not able to meet its timing requirements. So this specification will not work for the particular architecture that we're looking at. Now, on the flip side, you notice here, we had this thing go up to about 300. But now when we change this to reduce this to about 700 microseconds, yes, the CDT did not meet, but no in the buffer, which is dropped. So there was an improvement for the class for the CDT frame. Now, once you look at the network and you're happy with how the network has been configured and everything looks okay on the network, the next thing to look at is so once you've set up the network and you're happy with the network configuration to say, yep, this is my credit, this is my buffers, this is my routing table, this is the network bandwidth in each of the slots, then you want to come back and see how it works in a real application. So here, for example, we have a braking application, and you can see these are all the different sensors. And in addition to that, you can also see the ECU that's being configured, complete with the processor, the memories, the flash, the all of those attributes. So with this, not only are we creating the automotive network and the gateways and the multi-protocol systems, but also starting to incorporate the ECUs and all of those within the single configuration. Now, why is that significant? The reason it's significant is because the I'm not just dependent on the ECU. The application goes beyond the ECU. It goes to the how the sensors are positioned or where the sensors are positioned. It looks at where the ECU processing occurs. It's happening closer to the sensor or closer to the ECU. And also other attributes such as power consumption, heat displays, voltage, all of that type of information as well starts playing a major role. So for example, over here, when I look at the brake latency, you can see the red and front brake, those receive the data in a very, very small band of latency. But when you look at the rear brakes, you can see the range is pretty substantial. Here you can go 300 to about 400 microseconds, almost 33-34% difference between the best and worst case. So what we're seeing over here is that there is significant blocks or buffering or maybe something's wrong with the scheduling on the networks connected to the rear brakes. So that's something that needs to be configured. Everything looked okay when we sent the generic traffic, the trace fine to the real car. But now when we put it on the real network, things completely change. Now, all of these are pretty standard to most designers. You know, your network modeling, looking at the ECUs, looking at the hardware. Now, what was unique was that you combine the network and the hardware into a single model and also incorporated the tasks that go onto the hardware. Now, what changes significantly is this. With network systems engineering, it's no longer just the network, because apart from the routing table and the network configuration, the traffic traces, you have to now worry about the autonomous driving aspects. You have to worry about how these use set up, because that's going to determine your message passing across the network. But the big ones, cybersecurity, artificial intelligence algorithms, gates incorporating phasing systems. So when you run your test cases, you need to actually configure not just the automotive network, but all the other aspects. For example, denial of service. I incorporate a cybersecurity algorithm, which is AI-based. Now, Google offers me tools that can check to see if the algorithm is correct. But what happens when you put it on real hardware? All of these need to be studied in the network systems engineering process. Now, why do we want to do that? The reason we want to do it is because we're interested in getting the timing constraints to meet. For example, over here, T3 had to complete at this point, but in reality, T3 completed here. What was happening? It's all related to the slots. You can see over here, T1 here, we finished T3 over here, started expecting it to finish over here. But there was sudden T1 frame, which could have been a CDT or it could be a class A frame, and this could be a best effort. What happened was that this ended up taking much longer, and by that time, I'll say a class B frame came to be processed. So you can see we're using up these small slots here, but only after all of these cleared, you had sufficient bandwidth to get complete. So your software application one is data, and of course the hardware itself. The aspects of these systems today is that when you have harness, it was all very clear. When you had wiring harness, things were very easy. You had a bunch of wires that went point to point, so you knew that the only chance of failure is somebody physically cut the wire. But here, when you have an Ethernet, you can have a variety of failures. It can be a node failure, a connection, there could be dependencies, there could be connectivity, there could be a whole lot of failures. Just listed common ones that are supported in our environment. So what do these network failures mean? Some of the things may be that your latency is not met, packets are dropped, where you can see like right over here, you can have up to 90% loss in packets. Or it can be an overloading of a network. So a variety of failures can be evaluated. And only when you look at all the failures and you say, okay, for my, say, my braking application or my infotainment application or my safety, and I apply all these failures, does my cybersecurity system detect these failures? So when you're looking at your network, you have to consider all of these different aspects when you're actually assembling the system. Now, of course, you can build your own simulation model and incorporate all of these. But if you think about the amount of effort and time it will take to construct all of these, having a library of it would be far more useful. And that's exactly what we've done with VisualSim. So what we have is a network failure library. And what the network failure library does is it actually analyzes the different flows and it produces results, shows you what your latency is, when you had a failure, did not have a failure. So this was the normal flow. So that was a red and that was a blue. And this was when there was no failures. And this was when there was a network failure because there was a denial of service. And you can see what the range in the latencies and how the latencies were impacted. In this particular case, the congestion was at this node 2 that was generated. So our network failure module generates a variety, almost 10 different types of failures. And here what we're looking at is through our diagnostic window, getting to know what happens when those failures happen. So we created the network, we created these applications on the top of the network. Now we create these failures and then use our cybersecurity AI applications to really determine whether the failures are being detected, whether the failures are being overcome by the algorithms that we have developed. Current generation testing of the cybersecurity language or cybersecurity code is really limited to algorithmic correctness. So Google offers a lot of tools which you can use to check to see if your AI application is working. Now, you can create some simple traffic models using open source networking and bring in, say, a Wireshark trace file. But the what you really want is to expand to evaluate real-time network. What does that mean? Two things. One is these AI algorithms are running on top of a hardware, which is a gateway ECU. So what is the response time on the gateway ECU based on the application, based on the data type coming in, and based on everything else that's running on that ECU? So all of these things will impact not just the ability to handle the threat, but also the impact on your regular network throughput. So how does it impact my regular traffic? Because my routing, maybe my packing, unpacking, maybe a variety of things, maybe running on the same core, same processor core. So how is that going to impact my overall behavior of my system? So we looked at the network, we looked at a particular application which incorporated the sensors, ECUs. Then we looked at the failures. We looked at cybersecurity that algorithms that made sure that those threats were nullified. Now, these cybersecurity applications or these AI algorithms or autonomous driving are running on top of an operating system, typically AutoSAR or something similar to AutoSAR. So now, in addition to the applications, we also want to see what is the impact within the ECU on the configuration. So if I take my different buses, in this case, I got Canon Lin, I put my ECU gateways, and I start incorporating all the other hardware platforms. And this is my logical architecture of my different software tasks. I map them to different hardware platforms. So say this function here goes here. Yes, autonomous goes to this one, while autonomous driving 2 goes to the brake ECU. So you can assign different functions across the network. Now remember, when I put A- function here, 1 here, and 2 here, guess what happens? You have data transfer between these, and especially if they're video data or they're large number of sensor data, there's going to be an overloading on the network, which is going to cause performance bottlenecks, performance issues. So you want to be able to understand how the performance is going to impact your particular design or your particular system. So it's not just saying, oh yeah, I've got one ECU, I've got one sensor, I've got these multiple networks are connected to gateways. But now you also want to see how the application impacts the workload on your network. Get that view of your system as well. So here, for example, we have the hardware software mapping, which is CAN bus, has all the devices. These are the regular tasks within each of the devices. And then, of course, here we have those 3 different autonomous driving. Here, we are mapping each one to one of these different ECUs to try to see what happens on my network if I move these different tasks around. Earlier on, if you look at the old way of doing things, we'd say, oh yeah, let me put my sensor on this network, my ECU on this network, and I only care about the data movement between the sensor and the ECU. But now you have ECU to ECU type traffic, which is especially traffic, is going to cause a lot of system bottlenecks. So your allocation is not just limited to worrying about sensor to ECU and ECU back to attenuator, but rather it can be well as an incremental traffic. As mentioned, if anybody has any questions, go ahead and ask the questions so that we can incorporate them into our presentation. Now, this is not strictly on the networking level, but I thought I'll cover it anyways. The idea here is the fact that you're integrating your AutoSAR, your other operating systems, directly above the hardware platform. So now your cybersecurity or your AI or your autonomous driving or your braking functions are now no longer just running as a resource consumption of the processor, but rather running it based on a software scheduling. So your AutoSAR in this particular case would be the element. And of course, once you do that, you want to see, when you're ready versus ready to run and you actually start executing, what was the delays between each one of the runnables. And of course, you can see at what points the delay maximum or the delay minimum will reach. So delay minimum is where it goes less than the minimum time that you can that this has to finish. So it's actually finishing faster than you anticipated, which causes problems downstream for other software tasks. Now, we talked a lot about what happens inside the car. Talked about multi-protocol networks, talked about the mapping, talked about cybersecurity, artificial intelligence, routing. But now, today, most vehicles have more data going out from the vehicle than within the vehicle. So, for example, I could have an app on my electric vehicle which turns on my air conditioning. Or, for example, I could have an app which gives me statistics on like what is the engine movement, or how much of the bearings available, what's my tire pressure, variety of data that's also accessed. Which means that now I might have other services that I'm offering, which may require me to authenticate onto a data center, or might require me to send the data for processing in a data center, because more the artificial intelligence training and execution is over there, try to reason, then that can feed back into the vehicle itself. So what are the bottlenecks in these scenarios? So when I look at remote processing, there's my automotive network in the car on the left-hand side, have multiple interfaces that go into the data center where I could have large number of processors, solid state devices, multiple processors that, I'm sorry, multiple operating systems that are running on this hub. So it gets to now incorporate a simple resource of, okay, I'm just going over there, but now having to worry about how the data center itself is organized, because that again has a huge impact on the response time within the vehicle. So if I'm expecting the vehicle has to get a response time within 5 milliseconds, but I've got like 200 million cars right over here that are accessing this data center, is it going to be able to get that? So we want to be able to evaluate all of those aspects as well. So what do? You take the model. So for example, over here, you take the VisualSim model and you start incorporating not just your gateways, your TSN switches, but also look at the 5G networks. You look at the actual data center itself. So you can open this up and you can see more details of it communicating to the data center. So all of those, which is right over here, the definition is right over here. So you can see operating systems, processors, HPs. So now, not only are you within, they're also incorporating your 5G interfaces. So for example, if I go in here, I can see the 5G activity as well. And then of course, I can see the data center. So what is now happening is that I'm now looking at the end-to-end operation from the vehicle to the data center and back. And of course, there is also considerable where it can start becoming in seconds as opposed to micro or milliseconds. Throughput also drops quite a bit, 10 to the power 7. But you can see still what the gateway latency is, because it just goes across the latency. Now, you can also get for your particular requirement, what was a data center needs as well. No longer within the car, expands out all the way to the data center. So a quick introduction to mirrorless design. We've been around for many years now. We've been the electronics, semiconductor, aerospace, working, hardware, embedded systems. Now we're also been in the automotive industry for a couple of years now. One of the big things is every year we've been getting different types of awards. But in addition to that, we've been always innovating. We've always been adding new functionality and new mirrorless design. What it allows us to do is allows us to get more market segments where VisualSim can be utilized. This shows you a range of customer base that we have. Now, mirrorless as a company provides you the VisualSim software with all the libraries. So as you drag and drop those components, see the different components that are available that you utilize in the modeling, like 5G or TSN or a processor or memory or a gateway or a data center design, any combination of those. Of course, we also provide training and custom modeling services as well. Now, VisualSim is, as you saw, is a completely graphical environment, has a large number of libraries that handle all the different aspects that you'd ever need in putting your entire systems engineering design together. Of course, you do have the ability to analyze the end-to-end electrical engineering, not just the embedded systems down to the semiconductor level, but also be able to do functional safety analysis. This has shown you failures. Functional safety for ISO compliance can also be modeled within the same environment. Critical aspect of hybrid and auto and electric vehicles is really the power. How much of the battery is being consumed? What's the life cycle of the battery? How big a battery do I need? Making all of those kind of judgments right up front. Remember, I can create this big network. I can create the access to the gig, to the data center. I can increase the ECU. I can put the operating system on top of it. I can, create models of the applications to run on top of it. So essentially, now what I have is I've got a complete system for the for doing my entire model-based system design of my entire vehicle. So it's not just restricted to just the network or the ECU or the software, rather puts everything together. This just shows you the libraries in VisualSim. I'm not going to take too much time. Of course, end of the simulation, end of the presentation, you will get an email with the link to the presentation, also a link to the video as well. So ask the question, I'll be happy.